we will now discuss another important concept in thermodynamics, that is adiabatic expansion of a gas. What does this process mean? In an adiabatic process, heat does not flow into the system or out of the system. In other words, when we deal with the amount of heat added, there will be no amount of heat added in an adiabatic process. So that dq will be equal to 0. This is the most important characteristic of an adiabatic process. The amount of heat added will be 0. There will be no heat added. There will be no heat removed from the system. Now tell me, therefore, if a gas expands adiabatically, that means no heat is added or removed from the system. So when a gas expands, what is likely to happen? What does expansion mean? Well, expansion means the gas is doing work. Now, if a gas has to do work, it has to have energy. If no external energy is provided, where is the energy going to come from? It is going to extract energy from within itself. In other words, it is going to use part of its internal energy to do work in expanding. As a result, an adiabatic expansion will produce cooling. Why produce cooling? Because the energy needed for doing the work of expansion is taken from the internal energy, which will then reduce the internal energy and therefore produces cooling. In the same way, an adiabatic compression will produce heating. A very important concept to know these things. Since heat does not flow into the system during an adiabatic expansion, the energy needed to do the work to expand is derived from the system itself, from the internal energy of the system. We will obtain an equation for the adiabatic process using the equation of state. What is the equation of state? Well, of course, the equation of state is PV equal to nRT. And the first law of thermodynamics. What is the first law of thermodynamics? Anybody know what the first law of thermodynamics is? Yes? dq equal to du plus dw. And what is dq for an adiabatic expansion? Is 0. Alright, so dq equal to du plus dw equal to 0 for an adiabatic process. Alright, now, what is du? You remember du? du over dt is Cv. So du is Cv dt. And what is dw? dw is pdv. So this equation now becomes du becomes Cv dt plus dw is pdv equal to 0. And now we use the equation of state, which is PV equal to nRT. What can we do there? Well, we can find the value of PdV from there. Is that right? We can find P equal to nRT divided by V. So what happens if you replace this P by nRT divided by V? We have Cv dt plus P is nRT divided by V, and I wrote that V here as dV over V equal to 0. I hope you understood that. P is replaced by nRT divided by V. So you got Cv dt plus nRT times dV over V equal to 0. Now divide by Cv times T each term. What happens when you divide this Cv dt by CVT. You will get dt over t. There you are. CV dt divided by CVT is dt over t. What do you get if you divide nRT? Alright, let's take this one. nRT is divided by CVT. The t and the t will cancel. We got nR divided by CV times dV over V equal to 0. Alright, these are sheer mathematical manipulations. And of course, all physical principles are derived using mathematical principles. Alright, we can now, do you remember this nR is Cp minus Cv? You recall that one? Cp minus Cv equal to nR. And so this nR can now be replaced by Cp minus Cv. We have dt over t plus nR is Cp minus Cv divided by Cv times dV over V equal to 0. Alright, let's simplify this. Cp minus Cv all over Cv. We can now divide each term by Cv. This will be Cp divided by Cv minus Cv divided by Cv. And do you remember when we talked about the speed of sound? That was a few lessons before. When you talked about the speed of sound, I gave you an equation for the speed of sound. Does anybody recall that? Well, I must be joking. Well, speed of sound V equal to square root of gamma P divided by rho. Well, I hope it rings some bell. At that time I told you we will deal with that particular quantity gamma later on. And I gave you the value of that gamma there. I said use the value of gamma as 1.4. Alright, this is the time I'm going to introduce that concept of gamma. You know what gamma is? Gamma is the ratio of heat capacity at constant pressure divided by heat capacity at constant volume. In fact, gamma equal to Cp divided by Cv. That is the quantity gamma. And for a diatomic gas, Cp is 7 over 2 Nr and Cv is 5 over 2 Nr. Is that right? And Cp divided by Cv will be 7 over 5. What is 7 over 5? Is 1.4. And isn't that the value I gave you to use that time? Air. For most practical purposes, air is the diatomic gas and the value of gamma is 1.4. So, when you divide here, Cp divided by Cv, that Cp divided by Cv is that gamma. Okay, let's do that now. So, simplify this. This will be dt over t plus Cp over Cv minus Cv over Cv is 1 times dV over V equal to 0. And that is the ratio of Cp to Cv is a constant and is denoted by Cp over Cv equal to gamma. And so our equation now becomes, how does that become? It'll be, for a monoatomic gas, let's look at the value of gamma. For a monoatomic gas, Cp over Cv, Cp is 5 over 2 Nr for a monoatomic gas, and Cv is 3 over 2 Nr, and that will be therefore 2.5 divided by 1.5, or for a monoatomic gas, Cp divided by Cv, that is gamma, is 1.67. And for a diatomic gas, I just gave it to you, Cp is 7 over 2 Nr, that is 3.5 Nr. Cv is 5 over 2 Nr, and that will be 3.5 divided by 2.5 is 1.4. The value of gamma for a monoatomic gas is 1.67. For a diatomic gas, it is 1.4. So this Cp over Cv will now become gamma. So the equation for the adiabatic process now becomes dt over T plus gamma minus 1 times dV over V equal to 0. Well, this is a differential equation, a very elementary differential equation. We can solve this equation. Do you know how to solve this equation? dt over T plus gamma minus 1 dV over V equal to 0. The equation for the adiabatic process can be obtained by integrating each term of the equation. That's right. This can be solved by integrating each term. Let's do that. So integrating this gives, well, I'm assuming that you know these integrals. Tell me, what is integral of dt over t? We talked about that in the last class. Integral of dx over x is ln x. Integral dt over t is ln of t plus gamma minus 1 is a constant. So that would be gamma minus 1 times integral of dV over V will be ln of V is a constant. So integrate each term. That will give you ln of t plus gamma minus 1 ln V equal to a constant. Well, I can rewrite this. Can you use the properties of logarithms to write this? Gamma minus 1 ln V is the same as ln of V to the power of gamma minus 1. Is that right? Yes. So that will be ln t plus ln V to the power of gamma minus 1 is a constant. And now the left hand side is the sum of two logarithmic terms. Can you combine that into a single logarithmic terms? What is ln of t plus ln of V to the power of gamma minus 1? It will be ln of tV to the power of gamma minus 1. Log of A plus log of B is log of AB. So you have ln of tV to the power of gamma minus 1 is a constant. Now, watch this again. If ln of a quantity is a constant, then that quantity itself has to be a constant. Only if a quantity is a constant will ln of that quantity be a constant. So what is our conclusion here? tV to the power of gamma minus 1 is a constant. Now, this is one equation for adiabatic process. When you deal with an adiabatic process, by the way, what is the characteristic of an adiabatic process? The amount of heat added or removed from the system will be 0. The system is isolated. No heat get added or taken away from the system. For such a process, tV to the power of gamma minus 1 is a constant. What does it mean? It means if T1 is the temperature in state 1 and V1 is the volume, the state changes to T2, V2. It means T1, V1 to the power of gamma minus 1 equal to T2, V2 to the power of gamma minus 1. That is the meaning of TV to the power of gamma minus 1 is a constant. So this is one equation. We're going to get one more equation for adiabatic process. This is one equation. All right. But T equal to PV over nR, the equation of state. PV equal to nRT. Solve for T from there. We got T equal to PV over nR. Now, let's replace T here by PV over nR. And what do you get? That will be, this T will be replaced by PV over nR times V to the power of gamma minus 1 is a constant. Alright, tell me, what is V times V to the power of gamma minus 1? Well, I know some of you will have no problem doing this. V means V to the power of 1 times V to the power of gamma minus 1 is V to the power of 1 plus gamma minus 1 is the same as V to the power of gamma. So V times V to the power of gamma minus 1 is the same as V to the power of gamma. Let's rewrite that. Now, and also nR is a constant, is that right? This nR is a constant. So we can now multiply this nR with a constant, which will still be a constant. That means we get PV to the power of gamma. You see, V times V to the gamma minus 1 is V to the gamma. We get PV to the power of gamma is a constant. Why? Because nR is a constant. Now, this is the second equation for adiabatic process. So what are the two equations for adiabatic process? TV to the power of gamma minus 1 is a constant. PV to the power of gamma is a constant. Now, we will use any of these equations depending on what are the given quantities that we have. So, two equations for adiabatic process are TV to the power of gamma minus 1 is a constant. PV to the power of gamma is a constant. Tell me, if you still remember, what does this gamma represent? Gamma is the ratio of heat capacity at constant pressure to the heat capacity at constant volume, Cp over Cv. And what is the value of gamma for a monoatomic gas? The value of gamma for a monoatomic gas is 1.67. What's the value of gamma for a diatomic gas? It is 1.4. Okay, let's now talk about work done in adiabatic process. Do you remember the equation for work done in isothermal process? What is an isothermal process? Where the temperature remains a constant. And we derived an equation for work done there. What's the equation we derived? W isothermal is nRT ln V2 over V1. You see, you can't forget these things. I don't forget them. Well, you might say, I have been using them. Yes, that's the way to learn them. Use them. You see, solve problems, use them, and sometimes you can even dream about them. Yes, there's nothing wrong about it. You will not forget them. So, let's now talk about work done in an adiabatic process. Now, for any process, we have, since for an adiabatic process, the work done equal to 0, we have dq equal to du plus dw equal to 0. Therefore, dw is negative du. Is that right? Work done in an adiabatic process is negative of du. What does that mean? This is what I explained earlier. The energy for work done in an adiabatic process is actually derived from the internal energy. That means work done will result in a decrease in internal energy. dW is negative of du. Now that is negative. Now I hope that by now this is familiar to you. Du by dt is Cv. Therefore du is Cv dt. Now this must be, V must be the subscript here, C sub V dt. Now that will be negative Cv. Look at the way I'm going to write this dt. dt is T2 minus T1, the change in temperature. So work done in an adiabatic process is negative Cv times T2 minus T1. Well, if you want to make this positive, I can write this now as Cv times T1 minus T2. Tell me, if it is an adiabatic expansion, will T2 minus T1 be a positive quantity or a negative quantity for an adiabatic expansion? For an adiabatic expansion, T2 minus T1 will be negative. Why? Because an adiabatic expansion causes cooling. T2 will be less than T1. So T2 minus T1 will be a negative quantity. So let's write this using positive value equal to Cv times T1 minus T2. And that is a measure of the work done in adiabatic process. But T equal to PV over nR, the equation of state. PV equal to nRT. And so your T1 can be written as P1 V1 over nR, and T2 can be written as P2 V2 over nR. So dW, work done in an adiabatic process, is Cv times T1 minus T2 becomes P1 V1 over nR minus P2 V2 over nR. nR is a common factor on the denominator which you can factor out. Is that right? That will be Cv divided by nR times P1 V1 minus P2 V2. Now, do you remember the quantity nR? nR is Cp minus Cv, isn't it? Well, we can actually do that, but Cp minus Cv is this nR. We can replace it by Cp minus Cv. Therefore, dW, work done in an adiabatic process, is Cv divided by Cp minus Cv times P1 V1 minus P2 V2. Okay. Is it possible for us to write this quantity in terms of gamma? What do you think? How do we write this quantity in terms of gamma? What is the definition of gamma? Gamma is Cp divided by Cv. So, all you need to do is divide each of these terms. You see, divide the numerator and denominator by Cv. On the numerator, Cv divided by Cv will be 1. On the denominator, Cp divided by Cv will be gamma, minus Cv divided by Cv will be 1. Is that right? So divide by gamma the numerator and denominator. We get dW equal to 1 over gamma minus 1 P1 V1 minus P2 V2. And that is the expression for work done in an adiabatic process. Is it difficult to remember? Work done in an adiabatic process is P1 V1 minus P2 V2 over gamma minus 1. Gamma minus 1 is on the denominator. That's a very simple equation. And work done in an isothermal process is nRT ln V2 over V1. And these equations are very useful when we need to solve problems. Okay, I think it is time we can now solve a problem. All right. Okay, 1/2 mole of helium is expanded adiabatically and quasi-statically. Well, quasi-static again is that each stage of the expansion equilibrium conditions are achieved. That is the meaning of quasi-static process. So, expanded adiabatically and quasi-statically from an initial pressure of 5 atmosphere and temperature of 500 Kelvin to a final pressure of 1 atmosphere. Find A, the final temperature, the final volume, the work done by the gas, and the change in the internal energy of the gas. Okay, what are the given quantities? We are told that you are given 1/2 mole of helium. Now tell me, is helium a monoatomic gas or a diatomic gas? Helium is monoatomic, is that right? So number of moles of gas is 0.5. The initial pressure is 5 atmosphere. Initial temperature is 500 Kelvin. The final pressure is 1 atmosphere. And gamma is 5/3. How did I get gamma equal to 5/3? Well, helium is a monoatomic gas. It will be Cp. Cp is 5/2 Nr. Cv is 3/2 Nr for a monoatomic gas. So 5/2 Nr divided by 3/2 Nr is 5/3, which is approximately 1.67. All right. A, for an adiabatic expansion, what is the equation? Tv to the power of gamma minus 1 is a constant. In other words, T1 V1 to the power of gamma minus 1 equal to T2 V2 to the power of gamma minus 1. So this means that T1 V1 to the power of gamma minus 1 equal to T2 V2 to the power of gamma minus 1. Now we have T1, we have T2. Well, so what can we now find? We can find a relation between V1 and V2. Is that right? So we get T1 over T2. T1 divided by T2 is V2 to the power of gamma minus 1 over V1 to the power of gamma minus 1. Alright, that step is okay. Now, that will be T1 over T2 is, because the powers on the numerator and denominator are the same, I can write now this as V2 divided by V1 all to the power of gamma minus 1. What are we looking for? Find the final temperature. That's what we're looking for. Now, we also have, well, that means this is not enough for us to look at. We also have PV to the gamma is a constant. You see that? We got two relations for adiabatic expansion. One is TV to the power of gamma minus 1 is a constant. And that gave us this relation. T1 over T2 equal to V2 over V1 all to the power of gamma minus 1. Now we take the second relation, or second equation for adiabatic process. And that is PV to the power of gamma is a constant. That means P1 V1 to the power of gamma equal to P2 V2 to the power of gamma. And if you notice, we have P1, we have P2, therefore we can obtain a similar relation here also. What is P1 over P2 equal to? P1 over P2 equal to V2 to the power of gamma divided by V1 to the power of gamma, which is V2 over V1 to the power of gamma. Alright, now what do we have? we know P1 over P2. Don't we know that? P1 is 5 atmosphere, P2 is 1 atmosphere, so we know what P1 over P2 is. So what we're going to do is solve for V2 over V1. Can you solve for V2 over V1? Let's solve it from here. V2 over V1 equal to P1 over P2 raised to the power of 1 over gamma. I hope you understand that. You see, if you have x to the power 5 equal to y, then what is x equal to? X equal to y to the power of 1 over 5. You see, if x cube equal to 8, then x equal to cube root of 8. Now, cube root of 8, what is cube root of 8? Is 8 to the power of 1/3. So, that idea is what we have used here. Now, if we have V2 over V1 equal to, we have P1 over P2 equal to V2 over V1 raised to the power of gamma. Therefore, V2 over V1 will be equal to P1 over P2 raised to the power of 1 over gamma. Very important relation. Now, we know P1 over P2. Now, therefore, we can now use this in the second equation. Now, remember, our aim is to find T2, the final temperature. That is our aim. So, we used this equation, we solved for V2 over V1, and let's now go to this first equation and replace this V2 over V1 by this quantity. Alright? So, replacing this in the first equation gives me T1 over T2 equal to V2 over V1 now becomes P1 over P2 raised to the power of 1 over gamma. This quantity is sitting in place of V2 over V1, and that is now raised to the power of gamma minus 1. And now if you notice, using the power rule for exponents, if you raise an exponent to a power, what happens to the power? Multiply the power. So this will be P1 over P2 raised to the power of 1 over gamma multiplied by gamma minus 1 will be gamma minus 1 over gamma. Well, I haven't used any of the values so far, but I can use them now. P1 over P2 is 5, gamma minus 1, gamma is 5 over 3. So let's use that. P1 over P2 is 5 over 1. I'm using the approximate value of 5 over 3 as 1.67. Gamma minus 1, 1.67 minus 1 over gamma is 1.67. You can do this on your calculator, and that gives you 1.9. T1 over T2 equal to 1.9. Therefore, what is T2 equal to? We are looking for T2. T2 equal to T1 divided by 1.9. And T1 we know is 500 Kelvin. And therefore, T2 equal to 263 Kelvin. Now, this has been a pretty involved problem. I want you to look back. Let me quickly review that one more time. What did we do? We first took the first equation for adiabatic process. Tv to the power of gamma minus 1 is a constant. In other words, T1 V1 to the power of gamma minus 1 equal to T2 V2 to the power of gamma minus 1, and we found solved for T1 over T2 in terms of V2 over V1. Alright, in the second case, we took the second equation for adiabatic process. What is the second equation? What is the second equation? PV to the power of gamma is a constant. Now, in other words, P1 V1 to the power of gamma equal to P2 V2 to the power of gamma. There again, we obtained P1 by P2 in terms of V2 over V1. And then we solved for this V2 over V1 as P1 over P2 to the power of 1 over gamma, and replaced this V2 over V1 in this equation by that quantity. You see the manipulations that we did? And then you simplified it. We got this quantity, all the values here we know. That's why we came in there. And using all the known values, this quantity simplifies to 1.9. That is T1 over T2 is 1.9. T1 we know, therefore T2 is 263 Kelvin. Alright, look through that again. Do this on your own. Only when you do it on your own, you learn. Find the final volume. Well, we have the final temperature now, the final pressure, we have the initial pressure, final pressure, the final temperature, initial temperature. We want to find the final volume. What will we do? The ideal gas equation is PV equal to nRT. You see, we have PT, is that right? We have the value of P1, we have the value of T1. That means we have P and T, we can find the value of V. We need to find the final volume. That means we need to use the final pressure. What's the final pressure? 1 atmosphere. What's the final temperature? Is T2. And therefore this volume will be the final volume. Isn't that right? So V2 equal to nRT2 divided by P2. Since we are looking for V2, we got to use T2 and P2. And we have all these values. N is 0.5 moles, R is 8.314, T2 we calculated as 263 Kelvin, and P2 is 1 atmosphere. Always convert that to Pascal, and that gives V2 equal to 0.0108 meter cube. What is the next thing that we need to do in this problem? Find the work done. Well, actually we have all ingredients needed for the work done. Do you remember the equation for the work done for an adiabatic process? I thought it was a simple equation. Work done in an adiabatic process is P1 V1 minus P2 V2 over gamma minus 1. For that, we've got P1, we've got P2, we've got V2, but we don't have V1. That means we need to now go and solve for V1. Now, how will we obtain V1? Well, we have P1 and T1. If you have P1 and T1, we can find V1 using the equation of state. V1 equal to nRT1 divided by P1. Is that right? And all these values we know. T1 you know is 500 Kelvin. P1 is 5 atmosphere. Write that in Pascal. That gives me V1 is 0.0041 meter cube. Now you have P1, V1, P2, V2, and we have gamma. We can calculate the work done. Adiabatic work done is P1, V1 minus P2, V2 divided by gamma minus 1. But all we need to do is use all these values. Remember to do them in absolute unit. pressure must be in atmosphere, and volume must be in meter cube. So you can see what I have done. I have taken 1.01 times 10 to the 5 outside, so that I don't have to multiply for each. I'll be 5 times the volume is in meter cube minus 1 times V2. You see, P1 V1 minus P2 V2, and multiply that by 1.01 times 10 to the 5 divided by gamma minus 1, and that is 1471 joules is the amount of work done. Now this problem in fact consists of all the principles we discussed so far in adiabatic expansion. So if you can do this problem, you can do any problem. Okay, and finally the quantity of heat added, dq equal to du plus dw. Well, of course dq is 0 for an adiabatic process. So dw equal to 1471 joules. Therefore, what is du? du equal to negative 1471 joules. What does that mean? It means the energy needed to do this work is taken from the internal energy of the object. That means the internal energy decreased by that much quantity. When the gas did so much work without getting heat from outside, it took energy from the internal energy. Therefore, the internal energy decreased by that much quantity. Okay, let's do another problem. An ideal gas at a temperature of 20 degrees Celsius and at a pressure of 1 atmosphere is compressed to quasi-statically and adiabatically to half its original volume. You see, the moment you see half its original volume, you must say immediately, aha, V1 divided by V2 equal to 2. You see, that quantity come very handy. It is compressed to half its original volume, V1 over V2 equal to 2. Find its final temperature and pressure if CV equal to 3 over 2 nR, that is a monatomic gas, and CV equal to 5 over 2 nR, that is for a diatomic gas. Alright, let's pick out data. P1 is 1 atmosphere. T1 is 20 degrees Celsius, always converted to Kelvin. That is 293 Kelvin. V1 over V2 equal to 2. Is that right? The gas has been compressed to half its original volume. So the initial volume is 2 times the final volume. V1 over V2 equal to 2. Alright. Let's take case 1 where CV equal to 3 over 2 nR. If CV equal to 3 over 2 nR, then Cp will be 5 over 2 nR, and that means gamma will be equal to 1.67. Actually, we don't need that step. You know, for a monatomic gas, gamma is 1.67. So the only difference between A and B is that in A, gamma equal to 1.67, in B, gamma equal to 1.4. So I will only do part A. You must repeat part B using the different value of gamma. For an adiabatic expansion, alright, what are the equations for the adiabatic expansion? We got 2 equations. TV to the power of gamma minus 1 is a constant, or PV to the power of gamma is a constant. Now, which of that are we going to use here? Well, we're going to use TV to the power of gamma minus 1 is a constant because we want to find its final temperature. So we have the initial temperature, we want to find the final temperature, so we use TV to the power of gamma minus 1 is a constant. Now what does this mean? It means T1 V1 to the power of gamma minus 1 equal to T2 V2 to the power of gamma minus 1. Alright, now can you rewrite this equation in such a way that it will contain V1 over V2, because that is known to us. Can you rewrite this equation in such a way that it will contain V1 over V2? Yes, T2 over T1 equal to V1 over V2 to the power of gamma minus 1, isn't it? T2 divided by T1 is V1 to the power of gamma minus 1 divided by V2 to the power of gamma minus 1, which is the same as V1 over V2 to the power of gamma minus 1. You must have the ability to look at equations like this and rewrite them. So we have now rewritten this equation so that we have the quantity V1 over V2 introduced there. Now you know V1 over V2 is 2, gamma is 1.67, T1 is 293, you can find T2, you see how simple it is? Now, this will be 2 to the power of 1.67 minus 1 is 0.67. And what is 2 raised to the power of 0.67? Use a calculator for that. It is 1.59. So T2 over T1 equal to 1.59. Therefore, T2 equal to 1.59 times T1. And T1 is 293 Kelvin. So that will be 1.59 times 293. That is 469 Kelvin is the final temperature. Alright, to find the final temperature, we used this equation. Now, we want to find the final pressure. What would we do? Well, to find the final pressure, we use the other equation. PV to the power of gamma is a constant. Now, don't confuse between here. TV to the gamma minus 1 is a constant. PV to the power of gamma is a constant. Alright, let's do that. Using PV to the power of gamma is a constant, we have, how will this be written? P1 V1 to the power of gamma equal to P2 V2 to the power of gamma. There you are. Okay, can you rewrite this equation so that it contains the quantity V1 over V2? Yes, it will be P2 over P1. You can see here, P2 divided by P1 will be V1 to the power of gamma divided by V2 to the power of gamma. Or P2 divided by P1 is V1 divided by V2 all to the power of gamma. And now you know V1 over V2, you know gamma, you know P1, therefore you can find P2. So this will be 2, V1 over V2 is 2, 2 to the power of gamma is 2 to the power of 1.67. Use a calculator for that, that is 3.18. Therefore P2 is 3.18 times P1, and P1 is 1 atmosphere, therefore P2 is 3.18 atmosphere. Okay, that's a very neat way to solve problems like this. Okay, and now I told you I want you to do the second part on your own. The same problem, the only difference is the value of gamma in this case will be what? When CV equal to 5 over 2 nR, Cp will be 7 over 2 nR. It's a diatomic gas. The value of gamma is 1.4. So do that on your own right now. Actually, don't just go away. Just sit there and do the same problem on your own. Okay. Let's do another problem. A diesel engine adiabatically compresses an air-fuel mixture. You see, in the earlier class I told you, the class before that, I think, the working of your car engine. You see, during the time the fuel-air mixture is compressed, the compression actually happens adiabatically. There is no heat get added from outside during that time. The heat gets added only when the spark plug produces the spark and the explosion takes place. So the compression of the mixture is an adiabatic compression, and that's the reason why the temperature increases. Remember, an adiabatic expansion produces cooling, and adiabatic compression produces heating. Alright. A diesel engine adiabatically compresses an air-fuel mixture from its initial volume at a temperature at atmospheric pressure and a temperature of 25 degrees to 1/20 of its initial volume. So inside the cylinder, the piston moves so that the initial volume V1 now is compressed to 1/20th of its initial value. So tell me, what does that tell you in order to solve this problem? It gives you a very important quantity to solve this problem. It gives you V1 over V2. What is V1 over V2 in this case? It is 20. That's right. So P1 is 1 atmosphere. T1 is 273 plus 25, that is 298 Kelvin. V1 over V2 is 20. Okay. Gamma is 1.4. We consider air to be diatomic. Alright, what are we supposed to find? What is the final temperature and pressure? Well, the method is the same. To find the final temperature, we take the equation that contains the temperature. What is the adiabatic equation that contains the temperature? T V to the power of gamma minus 1 is a constant. So we pick that equation. And what does this equation mean? It means T1 V1 to the power of gamma minus 1 equal to T2 V2 to the power of gamma minus 1. And we need to write this equation so that it contains V1 over V2. You know how to do that, is that right? T2 divided by T1 is V1 to the power of gamma minus 1 divided by V2 to the power of gamma minus 1. Or T2 divided by T1 is V1 divided by V2 all to the power of gamma minus 1. We know T1, we know V1 over V2, we know gamma, therefore V1 over V2 is 20, gamma minus 1 is 1.4 minus 1 is 0.4. And 20 to the power of 0.4 is 3.314. Therefore, T2 is T1 times 3.314, and that is 3.314 times 298, that is 988 Kelvin. So inside the engine of your car, when the fuel mixture is compressed, the temperature increases to a very high value, and the pressure also increases. We're going to find the pressure now. We need to find the final pressure. How do you find the final pressure? In place of this equation, we now use the second equation for adiabatic expansion or adiabatic compression. PV to the power of gamma is a constant. And we have P1 V1 to the power of gamma equal to P2 V2 to the power of gamma, and rewrite this equation so that it is written that contains V1 over V2. What would that be? P2 over P1 equal to V1 over V2 all to the power of gamma. There you are. And now V1 over V2 is 20, gamma is 1.4. That is 20 raised to the power of 1.4. That is 66.3. Therefore, P2 is 66.3 times P1, and P1 is 1 atmosphere. Therefore, that final pressure is 66.3 atmosphere. Now look at that. Inside the engine of the car, or this is actually the case of a diesel engine, which is normally used in trucks and buses and so on. So when the fuel mixture is compressed to 1/20th of its initial volume, the temperature increases almost 3 times, and the pressure increases, you see that, 66 times. The pressure and temperature increases to great values, and it is at this high pressure and temperature that the spark is produced. Well, a diesel engine does not have spark. This high pressure is enough to produce the ignition. There is no need for sparks. A petrol engine has spark plugs to produce the spark, to produce the explosion, to produce the energy, so that the energy is supplied to the crankshaft. But diesel engines do not need the spark plug. The temperature and pressure will be so high when you compress it, the explosion will happen automatically. Alright, now we have done very many representative problems in adiabatic expansion. Well, please do all the homework and get back to me if you need help. There is one more lesson left in this Unit 2 in thermodynamics. Well, we are picking and choosing the topics so that we can accommodate different types of units in making up the course. All right? We will do one more lesson for thermodynamics and then go on to electricity later on. I will see you for that last lesson later on.